First off, I apologize for any background noises. My kids are home with me now, so doing this the best possible. So what we're going to be doing within this section is looking at solving exponential and logarithmic equations, which you can imagine is going to be certainly applicable as we get into the applications of logarithms and exponents with exponential growth, decay, and also logarithmic applications. So just the skills absolutely necessary to be able to deal with these types of physical and mathematical phenomena. So that being said, to introduce us to how to solve exponential equations, which actually you know already through the one-to-one property, which we'll see as one of the methods below, but there's a little more that we have to do because one-to-one's not going to always match up nice and neat. So for instance, if we look at letter A, this is a perfect example of if the bases are equal, then the exponents are equal. But when we look here at B, the problem is we can't get 10 into a nice base of 2. Like 8, we can get to the nice base of 2 to the third, but what about 10? Well, we know that x would be approximately about 3.1 because 10 is just a little larger than 8, so 2 to the 3.1 would be a little larger than 8, which would be about 10. But we, instead of just estimating, just like when we have like a linear equation, instead of like plugging in or estimating in our head, we need some formal mathematical process to solve. So that's what we're going to develop here. So first off, the first method that we said, if you can get like bases, you're simply going to use one-to-one property that tells us that if the bases are the same, then the exponents are the same. I'm just going to put exp for exponents and vice versa. That's method one. Always look for one-to-one property. The second is going to be called what we're going to call natural log both sides. We know what we do to one side, we do the other. So if when are we going to use this? And we'll see if 1 to 1. I'm just going to put OTO for one-to-one, or like. That doesn't want one-to-one. That wants like bases, which is essentially saying the same thing. If like bases are not possible, then we are going to natural log both sides. Remember, we don't say ln both sides, we say natural log. And then once we get into a nice neat exponent form, like for instance an a right here, let's say we can't get like bases, we are then going to simply put it into logarithmic form and then use change of base rule, base formula. Change of base formula in terms of natural log. We'll see what that looks like. So looking at A first, we want to see if we can get like bases. Well, we have a base of 3, and now our 1/3, which we could flip to 3 over 1 to the negative x, but 64 cannot be written as a base of 3, right? 3 to the second is 9, 3 to the third is 27, and 3 to the fourth is 81, so we're going to have to use method 2, which is natural log both sides. So this is what this looks like. Remember, it's okay to do whatever to an equation provided we do the same to both sides. So what it means to natural log both sides is to put a natural log obviously on both sides, but whatever you have within the initial equation goes into the argument in the logarithm, and just the equivalent property of equations, provided what you do to one side you do the other, that's mathematically accurate. So now we look at that and go, okay, well, I want to solve for x. Well, right here I think in my head, well, x is in the exponent of the argument. Well, now I can take that and move it out front. So we're going to do that. So we have x here, comes out front. That's gone. And now we have x multiplied by natural log a third, and natural log a third, it is some decimal. We don't know particularly what it is, but if we think about it as x multiplied by a number, we know then that's just a basic linear equation. To get rid of that number, we divide both sides by it. Natural log a third divided by natural log a third cancels, and we have x now equal to that right there, natural log 64 over natural log a third, and then we could just plug that in the calculator to get our exact or approximate answer. So we look at B, we see the bases are the same, E and E are the same, so we set the exponents equal. X squared minus 3 equals x plus 3. You go, oh, that's quadratic, move all terms to one side. factors that multiply to be negative 6 and add to be negative 1 would be negative 3 and positive 2. Set those both equal to 0. Since one of them has to equal 0, that's a zero product property rule. We got x equals 3 and negative 2. And then all I do is what is called eyeball checking, just by seeing if we insert that, that's not going to make an undefined value. It will. You could check it for sure to see, make sure it equals. If I plug in 3, 3 squared is 9, 9 minus 3 is 6. Over here, you plug in 3, 3 plus 3 is 6, so we have e to the 6, e to the 6, so x equals 3. Same thing would happen in negative 2, but again, particularly with the logarithmic equations, because that's when we'll get some undefined values depending on when we solve. All right, 8. How can we work on 8? Well, we have a power term here with a variable in it. So if a variable, in general in mathematics, if in general we have a variable inside of a term, in order to solve for the variable, we have to first solve for the term. Very similar to like if I had like 2x squared minus 1 equals 10, in order to square root to solve for the x term, you're going to have to get the x squared term first. So you add over 1, divide by 2, and then square root. Same idea is going to happen here. So if we have this, we have 8 multiplied by that term. That's just like 8a equals 20. So we're going to have to divide by 8 first. A very, very common mistake is multiplying the 8 times the 3. So one reason that's incorrect is basically what I just said, that it's important to solve for the term first before you solve for the variable. But it's the simple rule that if I multiply the 8 and it's violating the rules of, please excuse my dear Aunt Sally, because you have to take 3 to the exponent first before you multiply. That being said, we have 3 to the x minus 1 equals, reduce that would be 5 over 2. And there's no way we're getting like basis on that, so we're going to natural log both sides. This is our exponent now of the argument, so we're going to bring that down in front. So I have x minus 1 times natural log 3 equals natural log 5 over 2. No, 5 over 2 is all within the argument of the logarithm. So we have two options here. We can distribute in the natural log 3 or divide by natural log 3 and then add over 1. I'm going to divide by natural log 3. 5 over 2 divided by natural log 3. And then we would just have to add 1. And then we have x equals that. If we distribute it in, and then we'd have x natural log 3 minus natural log 3. Add over the natural log 3 and divide, it would be just a different form of this right here. In any case, if we wanted to approximate, you just plug that in your calculator and it'll give you approximating round accordingly. Over here, if you look at this, one of the most common mistakes on this is, for instance, like adding over the 5 and like natural logging, something like that. If you look at this, it looks very similar to quadratic, where you have our squared term here, or x term here, and then a constant, and that's in fact what it is. And what we can do is what we call a or u substitution. I'm going to use a. I just like using the variable a. And I'm going to make a equal to e to the x. Just for instructional purposes, I'm going to rewrite this term as e to the x squared minus 4 e to the x minus 5. Sorry if you can hear a tornado testing alarm is going off in the background. It's what, first Tuesday of every month. Yep, that's why. So instead, so now if I insert an a for e to the x, just to make it easier on the eyes, we're really not changing up the mathematics. Now if we look at this, this is much more palatable quadratic to look at. So now we have factoring it. Negative 5 and positive 1 multiply to be negative 5 and add to be negative 4. Set them both equal to 0 and solve. And note, we're not solving for a, we're solving for x, so we want to reinsert the e to the x. Now we look at that and we have e to the x equals 5 and e to the x equals negative 1. So if there's two ways you can think about it. You can natural log both sides. Okay, so if we and I'll do both. You can just fast forward if you got this. move the x out in front, and now we have x equals natural log e, or x times natural log e equals natural log 5. Now let's look at the term natural log. So what does natural log e equal? Well, let's think about it. E is our base, e is our argument, so that means e to what exponent would give you e? E to the first power will give you e. Therefore, all of this equals 1. So we just have x equals natural log 5. That's one way you could do it. The other way is if I come back to e to the x equals 5 and I just say, okay, well, first off, what I just did was method 2. Method 3 would just be putting this into logarithm form. If I put this into logarithm form, we have log base e, but we write log base e as natural log ln. And then our argument would be 5, and that would equal our exponent, which is x. And if you look in both cases, it gives you the same answer. So you can think of that as method 1 or method 2. Now on the second one, e to the x equals -1. What exponent can you take e to get a negative number? That's not possible, so that's an extraneous answer. We go ahead and cross that off. Okay, now moving on to logarithmic equations. If first one in the bell work, you go natural log x equals 4. Well, if I just put that into exponent form, because our base is e to the x equals 4, look at x is solved for, and then if we want the approximate value, just plug in our calculator and round accordingly. For d, we look at and that should have been b, that we have that rule of if our logarithms are equal the same bases, then our arguments are equal. So it's almost like the log base 3 part cancels, and we have x equals 4. So this, the reason I did this is helps uncover some methods here. Method 1, and I think for logarithmic equations, I think the solving aspect is a little more nuanced and requires a little more thought. I think it's pretty straightforward for exponential equations. But for logarithmic equations, if we can systematize it by creating methods, I think first off, if we have logarithm set equal a number, just like we have up here, a logarithm set equal a number, all we simply do is want to put it into exponent form. Put it into exponent form, you're good to go. Method 2, if you have log equal a number, you're going to exponent each side with the same base as the logarithm. And then you're going to get a situation like we had with the properties earlier in the unit. For instance, let's say if I have natural log x equals 4, and I raise both sides as part of the exponent of e, and then over here we have that situation where we have a log base a of x. Since these bases are the same, this whole term goes to the argument of the logarithm, which makes it x. And that would be e to the 4th, which gives you the exact same thing as up here. And in my opinion, I think just turning this into exponent form is a much more efficient and also conceptually manageable way of handling this equation than using this raising idea of raising both into the exponent of the same base as whatever this logarithm is. In this case, it was e. I haven't really found a case where this is super duper useful relative to others, but if we have an expression, just an expression, for instance, like this, log base a of 2, within a homework problem is provided, or on a test, provided these two bases are the same, we just know that's equal to 2. So it will be applicable if we have an expression, but in equation form, I just think method 1's best. Lastly, if we get to a point where we have logarithm equal logarithm and they have the same base, then all we're doing is cancel out the bases, or cancel out the base and the logarithm, and the arguments are equal. So that being said, let's look at what we have here, different examples. So A, we have a base of 10. We have a variable in the argument, and that's equal to a number. So that would be method 1, where you could just simply take the base of the logarithm, turn it into exponent form, base of the logarithm is 10, take it to the second power, set it equal to the argument, which is 3z, and now we simply solve for z. So 100, or 10 squared would be 100, divide by 3 to solve for z, and then so z would equal 100 over 3. Here we have the same thing. We have a logarithm set equal to a number, so the base of that logarithm again would be e. Just a quick reminder, anytime you see natural log or what looks like ln, that means log base e, so you have a base of e right here, e to the 5th power equals our argument, which is root x minus 8. And to solve for x, we're going to square both sides. Square this, that would be multiplying those exponents, that would give you e to the 10th. The root and the square cancel, so you're left with the radicand, the number underneath the radical, which is x minus 8. Add over 8 to the other side, and you have e to the 10th plus 8 equals x. You could have also originally taken this half exponent, move it up, move it in front, and then multiply by 2 on both sides, and then raise it e to the 10th equals x minus 8. You would have gotten the same thing. Over here, we don't have a logarithm set equal to number. We don't have a logarithm set equal to a logarithm. So we're going to have to use our condensing rule. So if we look at that, that would be the product rule, and that's in expanded form. So if we condense it, that will be natural log. Remember, when we condense, we multiply the arguments. And now we have a logarithm set equal to number. I'm going to run out of room. Just going to come down here. Our base is e to the 1st power, because our exponent is 1. And then that's equal to the argument, which is x plus 1. Now I look at that and we go, okay, well, that's a factor quadratic on the right. It's not set equal to 0, so we're going to have to distribute. X times x is x squared plus x equals e. And you go, oh, that's a quadratic. Oh, darn, it's got that e in that. How can I work with this? Well, I'm going to just subtract over the e. E is just a number. It's a constant. So that's our c of the quadratic. Here's the problem, though. What factors multiply to be negative e and add to be 1? Nothing. So we can't factor this, so we have to set it, use a quadratic formula, where a is 1, b is 1, and c is negative e. So we're just going to plug it in and see what happens. Opposite of b, which again would be opposite of 1, plus or minus square root b squared, which is 1 squared, would just be 1, minus 4 times a, which is 1, times c, which is negative e, all divided by 2a. 2 times 1 is just 2. Let's go ahead and simplify that. 0 equals negative 1 plus or minus root 1, and that'd be negative 4 times negative e would be plus 4e, all divided by 2, and that would be exact form. Oh, whoops. Oh, my goodness. That was pretty brutal right there. This should have been, it's not allowing me to erase. Those should have been x's along the way, not o's or zeros. Sorry about that. Poor tic-tac-toe reference. I want to say TikTok. Oh boy, where our brains go in 2020, right? Okay, so it should have been x's, not o's. And then we have, that's our exact form. If we want it, and on the test, a problem like this, you wouldn't have to put that in the calculator, but we could easily just plug that in with some, just be careful with that. Okay, so the demand you prefer, sorry, bad REB joke. The demand equation for a microwave oven is given by that equation. Find the demand for a price of $600. So when you're looking at like economics and products being created, demand for an item is correlated, it's not the fundamental reason, but the price of the object. So if if a price is super low, the demand is going to be high. But if the price increases, then predictably the demand would go down. So given data, you can create an equation like this. And then so we want to see, like, okay, so if we price it at 600, what would the demand of that be? And then, we can evaluate that from there. So let's look at this equation. Be interesting, and we could look at this graph to kind of get a more general idea. That's supposed to be e to the 0.004x to kind of see the trend in this, and that's what you do in economics in terms of using mathematics. So again, just like we talked about before, we need to solve for this variable first. So the way we're going to do that is solve for the e to the 0.04x term first before we solve for x.